Hey everyone, welcome back to the Explainer. So in our previous lesson, we unpacked the impulse response of a first-order system and saw exactly how it reacts to a brief, sudden jolt. Well, today we're taking our next big step, literally. We're going to derive the unit step response, explore what it actually means physically in the time domain, and then we're going to shift our perspective entirely to examine its frequency characteristics using Bode plots. It's a really fantastic journey from time to frequency, so let's jump right in.
Picture this. You flip a switch, you open a valve, or maybe you suddenly apply a constant voltage to a circuit. How does the system physically and mathematically react to that immediate sustained change? Well, that exact scenario is what the step response is all about, and we are going to break down the exact math behind it right now. All right, Section 1, System and Step Input. Let's lay out the basics.
Okay, let's dive into this. Here is the fundamental building block we're working with, the standard transfer function of a stable first-order system. We denote this as g of s, which equals k divided by the quantity 1 plus tau times s. Now, these two parameters, they dictate absolutely everything. K is our steady-state gain. Basically, it tells us the final level the system will eventually reach. And tau, that little Greek letter, is our time constant. You can think of it as the master of response speed. It tells us exactly how quickly the system gets to that final level. To see this in action, we introduce our unit step input. In the time domain, u of t equals 1 for any time t greater than or equal to 0. When we pull that into the Laplace domain, our input, u of s, becomes simply 1 divided by s. So our goal right now is to figure out the output, y of t.
Moving on to Section 2, deriving the response. Time for some math.
So, how do we find our output in the Laplace domain for a linear time invariant system with 0 initial conditions? Well, we just multiply. Y of s equals our transfer function g of s multiplied by our input u of s. Substituting our terms in, we get y of s equals k divided by the product of s and the quantity 1 plus tau s. Now, to bring this whole thing back to the time domain, we actually need to split this fraction up using partial fraction decomposition. This transforms our equation into y of s equals k divided by s minus k times tau divided by 1 plus tau s. From here, we can cleanly apply the inverse Laplace transform, and boom, there it is, beautifully boxed up for you. Y of t equals k multiplied by the quantity 1 minus e to the power of negative t divided by tau for t greater than or equal to 0. What this equation describes is a really smooth exponential transition. The system starts at 0 and just rises exponentially toward that steady-state value k.
Section 3, Time Domain Graph. Let's actually visualize what this math looks like.
Now, what's really interesting here is how clearly the visualization illustrates the role of our time constant, tau. Just look at the curve. At time 0, our output y is 0. As time stretches out toward infinity, the curve levels off, perfectly approaching our final value, k. But let's look at exactly one time constant. When t equals tau, our equation simplifies, and the response reaches roughly 63.2% of its final value. If you wait until 3 time constants, we're up to about 95% of k. You can also see the green dashed line mapping the initial slope of the response, which is k divided by tau. This visualizes a crucial engineering rule of thumb, guys. K sets your final destination, but tau dictates the speed of the journey. A smaller tau means a steeper initial slope and a much faster physical response.
Section 4, Impulse and Step Connection. Let's see how these relate. On the left, we have the impulse response we studied last time, that sudden spike that decays. And on the right is the step response we just derived. Notice the mathematical symmetry here. The step response is simply the time integral of the impulse response. It's accumulating that sudden jolt over time. Conversely, if you take the derivative of the step response, you get exactly the impulse response. It's just a beautiful, elegant connection showing how these two fundamental behaviors of linear time invariant systems are intrinsically linked.
So, we've seen how the system reacts over time, but to fully understand its dynamics, we need to change our lens. As the saying goes, now let's replace s with j omega to see the frequency response.
Which brings us to Section 5, the magnitude Bode block.
By substituting j omega for s, we get our frequency response function. To graph this on a Bode plot, we calculate the magnitude in decibels, which gives us 20 log base 10 of k minus 10 log base 10 of 1 plus the quantity omega tau squared. Looking at the plot, at very low frequencies, the magnitude is flat. It just sits at that steady-state gain, essentially 20 log base 10 of k.
But then we hit a critical threshold, the break frequency, labeled omega sub b, which equals 1 divided by tau. Right at this exact point, the magnitude drops to 3 decibels below our low frequency level. This is the famous minus 3 dB point. Beyond this break frequency, the system simply can't keep up with the rapid oscillations, and the magnitude rolls off steadily with an asymptotic slope of minus 20 decibels per decade.
And finally, section 6, the phase Bode plot. So the absolutely crucial point here is how the system's timing lags behind the input as the frequency increases. The phase angle, phi, equals the negative arctangent of omega times tau. At very low frequencies, the phase is basically 0 degrees. The output tracks the input perfectly in time. But watch what happens as we increase the frequency. When we hit exactly our break frequency, 1 over tau, the phase lags by exactly minus 45 degrees. And as frequency pushes much, much higher, the phase delay approaches an absolute limit of minus 90 degrees. This brings us to a massively important unified conclusion, because the break frequency equals 1 over tau, a smaller time constant, doesn't just give you a faster time response, it literally pushes that break frequency higher, giving your system a higher bandwidth. Time and frequency domains, they're really just two sides of the exact same coin.
We've now successfully connected the time domain step and impulse responses to the frequency domain Bode plots, all governed by that absolutely vital parameter, the time constant tau. But this leaves us with a pretty fascinating question. If a single parameter dictates both the speed of a physical reaction and the system's frequency limits, what happens when we introduce a second energy-storing element, like a spring and a mass, or an inductor and a capacitor? What happens next in dynamic system behavior? Well, that's exactly where we're heading in the next part of this series as we tackle second-order systems. If this explainer helped you visualize these concepts, please give it a like, subscribe so you don't miss the next step in our journey, and share your thoughts or questions down in the comments. Keep learning, keep questioning, and I'll catch you next time.